Ladies and gentlemen, welcome back to Lab 1, Number 1, Part F. And I've been waiting for this one because this one we're finally getting to trace through what the RPART algorithm does. And you can basically see what's happening behind the curtains, behind the scenes, so you have a better understanding of how this algorithm works. And you can see for yourself that although there might be several different steps, it's actually quite straightforward, and it gives you a better insight and idea of how this algorithm works and how it's less of a black box and gives you more intuitive understanding of how the model is being designed. All right, let's start off with the fact that we were talking about the complexity parameter, right? And again, this is something that gets kind of complicated for some people. Basically, what this means, again, is that you want, anytime you're adding complexity, or in the world of classification trees, anytime we're adding more splits or more branches to our decision tree, to our classification tree, there's more complexity. There's more complexity in the model. That's a bad thing, because what happens is you tend to run into the situation of where you have overfitting on your data. Yes, you could build a complex tree, many branches, many levels, that breaks down and predicts the training data really, really well. But what's to say that that does that same thing to test data? What's to say that does that to any live data that you're doing predictions on? Okay, that training data, remember, right out the gate, that training data is a subset of all possible data that will be passed through this classification model. So in the world of classification trees, we like to keep our trees relatively shallow so that they are general enough to be applied to all kinds of data that are similar to our training data, right? Not exact, but similar to our training data. Now, here we reran the M3 model, right? We created another model called M3. And basically this time what we did was we kept everything the same, but we changed the complexity parameter to 0. Remember, by default, it's 0.01. Okay? And then I graphed it. You'll notice there's no difference between the M3 and the M1, right? Because the CP, the complexity parameter is 0. And by the way, when we say that CP equals 0, we're basically saying that, hey, the additional amount of reduction in the relative error per each new split that we're introducing has to be greater than that CP value. So in this case, 0, that means we're not penalizing splits at all. If CP equals 0, we're not penalizing splits at all. If CP equals something greater than 0.01, that means we're increasing the penalization for every split we introduce into our model. The higher the CP, the shallower the tree will be. The smaller the CP, the longer the tree will be. Now, in this case, we made CP 0, and we have the same model. Why? What's going on? This goes to the fact that our pre-pruning parameters, remember, CP is a post-pruning parameter, because what happens is the branch happens, and then we cut it, and you guys see that in a second. But our pre-pruning parameters are still, max depth is 30, that's the max, that's by default, that's the highest our part will go. The min bucket is 7, and the min split is still 20. Right, so those parameters are still there, and that is why this model is still the same, right? But when I create a new model called M4, this is off the M2 model, and now what I'm going to do is I'm going to change the parameters, the pre-pruning parameters. I'm going to make max depth 20. Again, it doesn't really matter. We won't get that big. Min split, I'm going to change to 2. Min bucket, I will change to 1. Remember, again, by the way, that min split and min bucket, they do have some sort of relationship if you do not explicitly choose those values. Usually what they like to do is whatever the min split value is, they like to make min bucket 1/3 that, or whatever the min bucket value is, they like to make min split 3 times that, right? But if you specify both, then they'll just take the values we gave. So in this case, I specified both of them, and that's why min split is 2 and min bucket is 1. Now, notice here now, the model is finally different. Right? Notice now, the model is finally different. It's very different. We have a lot more different branches. And then when you run the print CP command here, the print CP command, that gives you my table that we see right there on the right side. So we have a lot more going on, a lot more splits, a lot more calculations happening. Now, we never really discussed it. We talked relative error, we talked about number of splits is, that's obvious. We talked about what CP is, right? This CP is basically, even though it has the same initial as our CP over here, this is really talking about the additional complexity error. All right, so this is what it is additionally talking about. It's additionally talking about the amount of additional complexity error. And that's why it tends to go to 0, because this will go as far as whatever we set CP to. Because we set CP to 0, it kept going. Now, we haven't talked about XOR error and what's related to it, the XSTD. That X basically stands for cross-validation error. That X, cross-validation error, cross-validation standard deviation. We'll talk about that later, right? That's our next. We'll talk about XOR and XSTD. For now, just take it as it is, right? Take it as it is. It has to go with the fact that we do again, something called cross validation with the data. It's basically how you break up the training data, and you're basically testing different parts of the training data against itself and seeing what the errors are, and then taking the average of it. Again, we'll work it out, and you guys will see a little clearer what it is. XOR and XSTD is something that tends to change from when you run it from instance to instance, because there is some random selection going on every time you run it, and that's why the numbers will change from time to time. That's why the numbers will change time to time. Now, the way it works here is, ideally, when you're doing classification models, data scientists, they like to relax the CP aspect. They do like to have it 0. They want to crank out even the pre-pruning parameters. I mean, if there's no explicit need to have a certain kind of breakdown when you're breaking out these sets, they like to be as lax as possible because they want a deep tree. And they want a deep tree because they want to find the optimal complexity parameter. They want to find the optimal complexity parameter. How would they do that? Well, if we look at our table right here, what's happening here is obviously you want your relative error should be less than X error. That's number one, right? In all our situations, not all, I shouldn't say. So in most of our situations, relative error is less than X error, okay? Except for this one right here, line 2. Line 2, it's not. But in most cases, it is. What we want to do is we want to find the smallest possible cross-validation error. Where's the smallest possible cross-validation error? Well, here it is. They're both the same, 0.09238, 0.09238, etc., etc. So there's two schools of thought. One school of thought is find the second to last instance of that cross-validation error, which would be this one, 0.015, right? Another school of thought is just find the smallest cross-validation error where relative error is less than the cross-validation error. That would be our fourth line. That would be our fourth line. I'm going to take the situation where we have the smallest cross-validation error, where we have the least amount of splits. So our smallest cross-validation error, where our relative error is less than that is line 4. That all the lines are satisfy the condition, right? But the one with the least amount of splits is line 4. And that gives me a CP of 0.0153846. All right, so that gives me that value. Let's go ahead and knock it out in R, just so you guys can see it. Let me zoom in a little bit. And I should have RPART in here. And now I could do my, the M4 model. Cheese, tilde, dot, comma. My data is going to be, I think, the same thing again. Iris R, it's just first row. First 105 rows. And the type will be, what is it? We should cover apply grab all this. Method is classification, remember. And we're good to go. Oops, let's do that. That's fine now. All right, so I have my model. Let's graph it. Remember, there's different parameters. I mean, there's different ways to customize your graph. I like the 101 style. And we get this big graph right here. I think so we can see more. It's still this. It's horrible. Zoom in a little bit. There you go. So if I zoom in, I think it's still I'm just trying so you guys can see it. It's kind of hard to see, but I mean, if you run it on your machine, you should be able to see the graph some more clearer. I was hoping to get it clearer, but it's kind of small. All right, from here, do the print out your CP table. Right, and here we go. Here we have our table, and just like before, this is slightly different what's happening here now. This is actually quite interesting. I now have, everything else was the same. Max step, min split, CP 0. But this time, I only have 2 instances of X error. 2 instances of X error. And my smallest one is going to be this one right here, the CP. In my slides, oops, right here, my smallest one was, oh no, I had 6 here too. All right, XX. All right, all right. All right, perfect. All right, so slightly different, which is good. And should it be, I should actually have the same values, data IRS. Class, max depth. This is interesting. Very interesting. We should have the same values here. So we do have the same CPs here. Oh, yeah, that's right. Cross validation error is slightly different. Okay, fine. Whatever. We'll just use this one. That's fine. All right, so in my slide, I used this one. In this example, I'll use this one right here. That's right. Like I said before, cross-validation errors will change from instance to instance. All right, so now look. I want to now prune. What the heck does that mean? That means once you make your deep tree, you want to go back and make it smaller. Right? We want to make it smaller. So first thing we need to do is we need the CP table we're going to use. We need the CP value we want to use right here, CP, right? Now that's a little bit easy to get. If I do $M4, this will give you all the different, whatever you want to call it, properties, functions, variables, all at your fingertips. We want this right here, CP table. When I click this part right here, I don't know if it does warnings, I just get the table part. This table is basically a 2-dimensional array. All right, it's a 2-dimensional array. So for this, my purposes, I just want literally that value right there, which is the 5th row, 1st column. 5th row, 1st column, and bam, I get that CP that I want. All right, here in my slides, what ended up happening is I took the 4th row, 1st column, because remember, my smallest one with the exchange error was this one, was on the 4th row, not the 5th row. So I took that and I called it M4CP. I put the variable M4CP. Right? And I'll do the same thing right here. I'll call it M4CP. Another way to do this, guys, if you want to be slightly more fancy, is that if I want the 5th row, right? I can also use a function called which.min. All right, which.min, which will give me the first occurrence of the smallest number. So if I do which.min x error, right, and I run this, oh, object, oh, that's right, this is a multi-dimensional array, so the first column, second column, third column, fourth column of the fourth column. Let's try that. Of the first row, actually it wouldn't work on this. I would actually have to give it the column here, so it'd have to be basically, I mean, if I wanted to get a little more fancy, let's do all the rows, 1, 2, 3, 4, fourth column. All right, fourth column is 1, 2, 3, 4, x error. So the x error values. And then if I did this, this is the right way to do this. This actually gets more complicated. But which.min, and what which.min does is it gives me the index value of the smallest number. So that's why it gives me the number 5, because number 5 here is the first occurrence of the smallest value, fifth row. So I can literally say, there, CP row. And that way I could just be a little more dynamic, and I'm just showing off a little bit. And now I have my M4CP equals M4 $CP table bracket CP row. See, instead of just putting 5, I put the variable that I got dynamically, comma 1. So line 9 and line 7 is the same thing, except I did a little fancy work to dynamically get what was the first occurrence of the smallest value, or what is the row of the first occurrence of the small value. Right, now I have M4CP, and now I have the CP I am looking for. 0.00769238. All right, in this case it was 0.0154386. Now that I have the CP, I'm now going to take my model and the CP, the new CP that I want to prune by, and I'm going to use a function that's called, surprise, prune. And it's literally going to prune or cut off the branches that violate that CP value. Because remember, when we created M4, right, I'll call this pruned.m4. When we created M4 was CP0, we let that sucker grow. Now we're going to cut those leaves off, right? We're going to cut those leaves off based on that new optimal CP we found. All right, and first we give the tree, which is M4, and then we give the CP value, which is M4CP. I run this, and now I have a new model, pruned M.4. Let's plot this. Oops, this is too small for the graph, so I have to give it more space. And boom. All right. So in this case, what happened was I got smaller branches. I got less branches. So I got less branches. But in my slides, what happened was 1, 2, 1, 2, 1, 2, 3. So 4 levels here, and here I have 1, 2, 3, 4, 5 levels. So that difference between 0.07 and 0.015 did make a slight difference, did have a slightly more of a branch. So this has more complexity than this one does right here. But nevertheless, we pruned it. In this example right here, when I pruned it with the third highest number and only got four rows, obviously 4 levels, right, as opposed to 5 levels right here, right? You can see how it went ahead, chopped it up, and gave me a whole new graph that is similar to what we had before, with a little more variation. For example, now we have petal length and petal width involved, right? Petal length and petal width involved. So this is how data scientists basically play around with your classification models to get a better fitting model. I mean a more generalized fitting model. Sorry, a generalized fitting model. They start with something that's very specific, and then they like to prune it back using the prune optimal CPs and the prune factors, right? Optimal CPs and the prune functions, I should say. Optimal CPs and the prune function. And now here I'm doing a comparison side-by-side comparison, and you can see it's much better. Now, the accuracy of our original model was, did I do it right here? Oh, let me show you, I didn't do the code, but we can do it. I can do the code for you right now. But if you saw the original M4 model, or M2 model, the accuracy was 95.6%, all right? And if you look at the pruned M4 model, it is smaller, meaning it's more general, and it has the same accuracy. So what's the better model? It's right in front of you. Same accuracy, but less fitting all day, every day, people. All day, every day. And for my modified one right here, right, we want to do a predict. I use the predict model. All right, I'm predicting using prune M4. And my actual values or my testing data will be data iris. What is it called? Scroll down. Iris .r, but this time 106 to whatever it was, I believe 150. All right. And then my class equals, or my method equals class. Go ahead and I will call this these values are going to be the predicted values. So I'll call it predicted dot. This is getting kind of crazy, but predicted dot pruned dot M4. All right, so I have my values. You can verify that. All right, here's all your predictions. Alrighty. Okay, now from here, after we did the prediction, right, we now want to go ahead and take our actual values, which are in irsr dot the species column. So now we're going to go ahead and use a table command. I'm going to put the actual values in my first parameter. And now predicted values. Ooh. Do I have different lengths? Oh. I have 105 rows. Jeez. So make sure I'm using the right parameters. Oops, I think it's the wrong function. I should be using my predict. Yeah. Oh, type. Maybe type people. That's why I was getting crazy here. All right. That looks much better, but it still looks like 105 rows. We'll see what's going on in a sec. I think I know it doesn't like the data. I guess the data field doesn't like either. All right. Okay, finally, that's what I want. Excellent. I guess data, that's very interesting. The data keyword is messing it up. Maybe it doesn't exist in the functions, so it's getting confused. All right, so now we're ready to go. All right, let me do my predicted. And now I have my table. All right, now I have my table. This is my confusion matrix. What's the accuracy here, guys? What's the accuracy going to be? Actually, let me save this. We'll save this as confusion and for PM4. All right, so that's basically going to be my my confusion matrix. And if I just want to calculate the accuracy, what's the accuracy again? Class, what's the accuracy? The accuracy is basically the summation of the diagonal values, which were predicted correctly, right? Which were predicted correctly. I believe there's a function. I may be making this up, but I believe there was a function that allowed me to add up diagonally PM4. Let's see if it allows me to do this. No, I guess I think I'm making up Python stuff here. Right, but I thought there was a function that allowed me to add up diagonally the values, but I guess not. But mathematically, it's very simple what we have to do. I think there is a function that allows you to do it. I'm drawing a blank right now. Right, so let me see if I do look it up real quick. All right, yeah, so it's diag. Oops. The diag, this function right here will give me the of the value. All right, so let's try that. If I do diag cf.pm4 cf. Okay, that's the values I wanted. Right, so if I type in again, cf.pm4, you guys can see this nifty little function gives me the diagonal values, right, 23, 11, 9. And because it does that, I can simply do the summation of this, and my numerator is 43, and my denominator was going to be the rest of the numbers, and I just simply have to do sum. I can do sum of the whole stuff, and that will give me the summation of the denominator. I run it, bam, I get 43, which is divided by 45, and it's basically the same thing as these guys, 95.6%, which we knew we were going to get because I knew this one was 95.6, this was 95.6. That model seems right in the middle, so we knew we were going to get that. So there you go. That is basically how we go about creating these generalized trees. I mean specific trees, detail-oriented trees, deep trees, and then how we find an optimal CP value, and then we scale it back. All right, we scale it back. Now, we are finally, now that we understand complexity parameter, we are finally ready to do the RPART algorithm. In this case, we'll do the first steps of the first split of the RPART algorithm, and then leave the rest of the splits for you guys to check out and have a good time with. All right, because already I know this video is going to get, with these slides, this video is going to get kind of large. So, all right. So for our analysis, we're going to start with the, basically the, the same parameters as the default parameters. All right, the same parameters that, as we got in our default parameters. So basically our min bucket will be 7, our min split will be 20, our max depth will be 30. We'll take default. Our postprune parameter will take default 0.01 as well. You guys can tweak that if you want. But we're going to take the default, and we're going to work through the algorithm with these default parameters. Now, as recall from before, we have 4 columns, right? We have 4 columns. We have sepal length. Let me open up data train, sepal length, sepal width, petal width, right? This is our target categorical column. This is why it's a classification tree. These 4 columns are numerical. All right, they're numerical, which means what? It means we have to go through every unique value for all 4 of these, every unique value, and find the splitting function or the splitting value that will give us the smallest Genie impurity score. Now we're going to use data train, the data train table. Remember, the data train table was basically, all I did was, I basically set, let me save this actually, before I lose it. I'll call this BML Lab E, Lab 1E, all right? All right, so I think I did it before, but I'll do it for you guys again. I just created a new table that's just going to be iris.r, the first 105 rows. It's just easier for me to work with that way. All right. So we use the data train model to train it, and we'll go from there. Now, we're going to go step by step, column by column. We'll start with the sepal.length column first. All right. With the sepal.length column, we want to first look at all the unique values. All right, that we'll be doing. Remember, we need to go through every unique value. The table command, there's several ways to do it. The table command is a nifty way to do it. So if I do data.train $, it gives me a list of all the columns. I'll literally do the first one, which is sepal length. We'll go by this order: sepal length, sepal width, petal width. All right. Bam. Alrighty. I got all my unique values here. All right. So, but am I going to try all these unique values? Am I going to try 4.3? Am I going to try 4.4? Am I going to try 4.5? The answer is no. And the reason is because of our pre-prune parameters. We have to take that into account. What are the pre-prune parameters saying? Well, they're saying that when I make a split, right? For example, if I did a split on 4.3, when I choose 4.3 the splitting error, the 2 rules will be less than 4.3, greater than equal to 4.3. If I'm choosing all the values that are less than 4.3, what values do I have in sepal.length that are less than 4.3? 0, none. It's going to create a node, child node, that will have 0 values. That is violating my min bucket rule. The min bucket rule says that when I do a split, so here, data train is our main table, that's the root node that we're splitting. When I do a split, each child must have at least 7 values. Now the first rule, actually, that we should look at is min split, right? And what's min split basically means that whatever node you're splitting must have a certain amount of values. Our default value is 20. Our data train value has, if you look over here, it has 105 rows. We're good there, right? If I literally do, you can see right here it's 105 rows, but if you don't trust me, again, if we just do nrow data.train, you got 105 rows. You're good, all right? So from here, that's that. So the min split parameter is satisfied. The min, now for each rule, for each splitting value, we must check to see if the min bucket rule will be satisfied. 4.3 does not satisfy it. Less than 4.3, that child node to the left will become 0, violates it. Okay, let's see 4.4. Okay, how many values do we have less than 4.4? 1. Exactly 1 value. Right? That violates it again. Remember, it has to be at least 7. All right, 4.5. How many, if when we do less than 4.5, the left child node, right? If I go here again, right? This is what I mean by the child node. You have your root values, which is data train, and if I do less than 4.3, it's 0 values. Greater than 4 equal to 4.3, we're good. It's 500 values. 4.4 again, less than 4.4, that's the left child node. It's just going to be 1 value. Over here, 4.5. To the left of 4.5, you only have 2 values. Whatever's less, the values less than 4.5 or 4.3, 4.4, there's just 1 occurrence of each one. That's only giving you 2 values. That also violates it. We cannot choose 4.5. Let's go to 4.6. 4.6 right here. How many values are there less than 4.6? 1, 2, 3. Again, that is violated. All right, let's go to 4.7. If sepal.length is less than 4.7, how many values will be in this child node? 3 plus 1 plus 1 plus 1, that is 6. It still violates it. It's not until we get to 4.8. 4.8, sepal.length less than 4.8, okay, that we finally get 1 plus 3 plus 1 plus 1 plus 1. It is not until we get to 4.8 that when we do sepal.length less than 4.8, we get 7 values. We'll get 7 values here. And finally, our min bucket rule is condition is not violated. And obviously, when sepal.length is greater than 4.8, we get a value of I think 97 values, right? So obviously that's not violated as well, right? That's not violated at all, and you can see that here. So when we do ahead and we split the code, or I'll do it here for you guys. When you go ahead and split the code at 4.8, now literally I'll call it, what did I call it? A left node, right node? And I simply say, hey, sepal.length is less than 4.8. And sepal.length is greater than or equal to 4.8. All right? So when we do this, if you view left node, it's a table now. Let's go ahead and view it. We get exactly 7 rows, right? We get the 4.6s, 4.3s, 4.7, 4.4, 4.5. We get all the rows where sepal length is less than 4.8, and there's 7 of them. Basically, it barely makes the cut, but it makes the cut, right? Same thing with the right node. If I click on the right node, there's 98 observations, everything where sepal length is 4.8 and greater, right? And now we have our 2 data sets or 2 children to work with, and this obviously makes the cut. All right, so that's what we're saying here. And the breakdown is all of the 7 that are less than 4.8, they're all setosas, right? And where it's a mixed bag when the length is greater than 4.8. For this is our first splitting value that we're testing. Let's go ahead and test the calculate the Genie impurity score now, right? So if we calculate it, here I ran the table so you have the breakdown, unique breakdown. Okay. So for left node, it's easy. 1 minus 7 over 7 squared equals 0. Done. And obviously, because setosa is perfect, that's why the impurity score is 0. It's obvious. Here's slightly more complex. In total, we have 20 plus 38 plus 40, 98 values. They will be the denominators. And then we're going to divide by 98 all these unique values. So 20 divided by 98, square it. 38 divided by 98, square it. 40 divided by 98, square it. Subtract all these values from 1. We get the Genie impurity score for 0.641394 for the right node. Now the weighted average Genie score for this particular split on this value, the 4.8 value, is going to be 7 divided by 105. Why 105? Because altogether there's 105 values. All right. So 7 were here. So 7 divided by 105 times 0, because 7 of the values had a Genie score of 0. And then 98 divided by 105 times this value, 0.641394, because 98 of them had that impurity score. We take the weighted average, we have this Genie impurity score. So for 4.8, the 4.8 splitting function, the Genie impurity score is 0.5986395, whatever. Bam! Got it! All right, we got it. All right. So that was for 4.8. We now have to do for 4.9, 5, 5.1, 5.2, etc., 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 etc. All these numbers up to 7.3. All right. At 7.3, remember 7.3, less than 7.3, I'm good. I satisfied the min bucket rule. Greater than greater than equal to 7.2 is what? It's going to be 1 plus 1 plus 1 is 3. 3 is 6 plus 1 is 7. Excellent. 7.3 makes the cut. But when I go to 7.4, greater than equal to 7.4 is going to be 1 plus 1 is 2. 2 plus 3 is 5. 5 plus 1 is 6. That node, that right node, now not the left node now, but the right node, the greater than equal part of 7.4 will be 6 values or 6 rows. That's going to violate the min bucket rule. So we're only going to test from 4.8 to 7.3. I already did 4.8 for steeple.length. I got to do all these values. All right? I got to do all these values. How I'm going to do it? You best believe I'm going to use R to do it. All right? Even though we're working this through by hand with no need to give ourselves all this kind of pain, we're going to go ahead and use R to do it. So the first thing I want to do is I want to filter my values for only I want to filter my unique values for only the values that are not going to violate my min bucket list. So the 4.8 to 7.3, they're good. That's what I want. So I'm going to go ahead and filter for that. So let me go ahead and create something called sl.array for steeple.length. And this is basically going to be so do I name it something? All right. So actually I use the data table now to do it. Excellent. All right. Perfect. So let me show you step by step how I do that. So I have data.train and I want steeple.length to be greater than or equal to 4.8. Now I'm filtering just for the unique values I want. And steeple.length to be less than equal to, what do we say? 7.3. Right, so I want this range, 4.8 to 7.3. Right, this gives me a massive amount of table of values. So what I want to do is I just want to get the steeple.length values. Right, now I got all the steeple length values, but look, I just want the unique values, right? So in here now I say and now I got the unique values, but it's still kind of out of order. I want it in order. And so in my slides, what I do is I save these values to a vector, and then I sort the vector. But I could also do this in one shot right here. I could just pass in to the outside the sort command, and sort command works by default in increasing order. Right, so I could just pass it in right here, and now you'll see it gives me the values in proper order, just unique values. And now I'm ready to go. I will call this set of vectors sl.array for steeple length. Oops, done. I don't know why it keeps doing that weird stuff. And you can verify it right there. All right, okay. So I got my unique values. Now, you guys saw before what I did with the 4.8. We got to do that again. But now I want to do it for every value in this vector. Every value, not just 4.8. We want to do it for every value in this vector. Oh, God, what are we going to use? It's called a for loop. Right, we're going to have iterate through every value in our sl.array. But before we do that, we want to create the meat of the loop first. So what I'm going to do is, I know my iterator is going to be for I in sl.array. Right? I know I'm going to use that. I'm going to do something like this. Right? I know it, you know it, I know it. I will take on every unique value in sl.array, which will be 4.8, 4.9, etc., etc. But I want to build out the meat of it first before I put in, before I put into iterator. So I'm going to cheat And I'm going to, outside of this, I'm going to say I equals SL.array, the first value. Obviously, line 33 I will delete once I have everything going, right? But I want to go ahead and create an I so I have something to work with. And you'll see it's 4.8. From here, right, I want to create my left node, just like we did before. I want to create my left child and my right child. Left.node is going to equal data.train, where sepal.length is less than I. But we're now going to be take it slightly more fancy, because we know that we want to get the unique count. We want to get the unique count. So now I'm going to use my more advanced features to get not just the whole table, but I'm going to take the count of each unique values. Do you guys? Hopefully from ABI you guys remember how we do this. First, I'm going to use a new parameter called .end, and what this does is, if I just run this part, this is going to go ahead and give me the number count of all the values that are less than I in sepal.length. Okay, it's going to give me all the rows. So if I were to do sepal.length less than I get 7 rows. We know this already. But what I want is I want the count by species, right? So if I add by equals species right here and do this, oops, let me run this so you can see what I did. It literally now breaks it down for me. Like, look, by species, the number of rows you had was 7. We only had 1, Satosa. That's fine. So that's what left node is. Left node is now a data table, right? With, in this case, however many rows there are of classes there are in that node, plus the 2 columns that tells you what species it is and the number of values. So in this case, I have N7. I'm good to go. This is not that impressive because it's just 1 value. But if we do this for right node now, oops, what's going on here? All right. If we do this now for the right node, notice the changes I have to do. Obviously, I have to change that this is the right node. And I have to change the fact that it's now not less than I. The right node is now greater than equal to I. Dot n by species is the same. I run it. Now if you check out right node here, guys, boom. Right, so now right off the bat, we got the species in there. We have all 3 species, but now we have the count of each one. And this is happening because .n counts the number of rows, but by equal species forces the count to count the number of rows by the individual species, by the species column. All right, sweet. So we have now our 2 nodes. Now what do we must do? Now we gotta calculate the Genie scores for each one, guys. We gotta calculate the Genie scores for each side and then get the weighted average score. All right? So how do we do that? Again, it's quite easy. Right? Very, very straightforward. So there's different ways to do it. Let's do it side by side. All right, so left node, I'm going to show you, I show you 2 different ways in my slides to do it. Alrighty. Right node. Let's see the values again. You have your, think about how the math works, the equation, right? It's 1 minus p to the power squared for each one you're going to have, right? So if I have the right node, I'm going to have to do it for each one of these 3 species, right? I have to literally do 20 divided by 98 squared minus 40 divided by 98 squared minus 38 divided by 98 squared. All right, so I have to do that. Well, let's start off with what 98 is. 98 is a summation of all the values in the column. So I'll start with creating a column called n, or big N. That is basically the denominator, or I'll call it denominator. That's just going to be sum of all the n, right? I do this, now write that node. I got that now. Excellent. So now I just have to divide the fraction. All right, and I'll call this P for basically proportional probability, and this is going to be n divided by den, because now it's just row-wise math happening here. So in this first case, we have 98 for each row, because what's happening is because I summed up the column 98, it's just one number, and for all the rows, when you're creating a new column with just one number, it's going to create that new column and give each row that number. So that's what ended up happening here. Sum n literally just giving you one number, 98. So that one number has to go for every row, 98, 98, 98, which is what we want, because now we could do row-wise math. And now P is going to be basically n 20 divided by 98, 40 divided by 98, 38 divided by 98. It's now going to be row-wise. Each unique value will be divided by 98. So now I have P. Right, again, if I type in right dot node right here. Right, you see the P right there, you see the proportion. 20 divided by 98, 40 divided by 98, 30 divided by 98, right? Excellent. All right, so you see that, it's very straightforward. And then from here, what do we left to do? We got to square it. No problem. I'll call this P dot SQ for squaring it. I'll just take P and I'll square it. Right. So I got the P square there, and now I got the values I need. Right. So now I divide. I got the 98s. I divided 98 by each occurrence of each species, and then I squared that fraction. That's what P dot square is. Now I just got to subtract those values. Real easy. I'm just going to do, that just ends up being all the rows, 1 minus sum, or if you want to do like that, sum P dot square. I get that number right there. So if I simply do 1 minus whatever that is, I get the right side. Guys, and by the way, we're just reworking. This is the first value is 4.8, so we're reworking what we did before. So this literally gives us the right side, which is 0.643994, which was the value. Oh, the 6413994, 6413994, which is basically the right side value, right? Another way to do this, by the way, is instead of doing 1 minus, I could have done that all in one. I could have literally done what I was doing that before. 1 minus sum. It gives the same value. Alrighty? And now we got our right side. And I'll call this literally right.genie. I know in my slide I call it right.node.genie. So, and on my left side, I'm going to call, I got to now do the left side, right? But left side, I think I'll do it all in one shot. And this is what I showed you in the slides. I can go ahead and combine all the lines we did. I believe lines 38 to, yeah, even lines for 30, I think lines 38 to 41, we can combine all in one line. So if I do left.genie will be left.node, all 1 minus sum of, oh, get carry. All right, so let's do this first. Let me get the denominator again. I think that's easier. All right, I think from there, oh no, I didn't have to do that, hold on. Could have still done this, right? Combine that, and then I could have done squared it. Right? And then these values could have been summed up. Right? I'm just combining literally row 38, 39, 40, and 41 into 1. And now I'm just going to do 1 minus this monstrosity. Oh, I don't want to call it den. I actually want to call it something. I want to call it anything. I want the number, actual value, which is 0. It gives me the value 0. All right, and this becomes, and that's the right answer. We know the left Genie score is actually 0. All right, and now our actual Genie score, called GS, is going to be, well, we got to do some math here now. Okay, we got to do some math. So my data train value, all right, the actual values in data train, we'll call that total n, or total.n, equals data.train, all the rows.n. And that'll give me, that should be now 105, all right? Now I need the left child and right child, so right.n equals right node. We know how to get that, all the rows.n. Right, and that'll give me 3 values. Whoa, 3 values? Nope, that's not what we want. We don't want .n, we want, remember, right node, if we just highlight this part, is literally 3 rows, but we want the summation of the ends. So here, I'm going to do sum Alrighty, so right.n, 98 values, that's what we want. And my left one is left.node sum n. Seven values, excellent. All right, now we are ready to calculate our Genie score, our weighted average Genie score, which is going to be my left side, what do I call it, left.Genie. Actually, it's going to be left.n divided by total.n times left.Genie plus right.n divided by total.n times right.Genie. Type GS now. I got my 0.59863995. And basically we did the same calculation right here. This line 51, right? Line 51 is what we did here. The weighted average score here. Boom. I got the right value. Now, the one last step that we have to do in the for loop, I will do that in the for loop. But now what we want to do is we want to take this monstrosity we just created and put it in the for loop to calculate for all the values. All right, so I'm not going to take line 33 because I will be automatically given for us in the for loop. I'm going to take this. I need this. I'm going to take the left. I'm going to use this value anyway. And this style of calculation is just easier. All right. I have the left node and I will do the right one. Let me change this for the right one. Doesn't require much. This requires me to do right there, left Genie, right Genie, right? So now I have those values, my right Genie, left Genie. And now what do I need? I need my ends. It looks worse than it is because I kept doing sanity checking. All right, this one, this one, and this one. So I got my ends with my different numbers. And finally, I got my weighted average Genie score. Now, for any guys following along, what's going to happen to GS for every unique value in sepal.length? It's going to keep getting overwritten, right? We need a way to store that GS value. So that's why I introduce another vector called Genie.scores. It'll be empty. Right? That I created an empty vector, and now what's going to happen is I just want to use that to store the GS every time it's run. So I'm going to literally keep appending to it. I'm going to use the C function, and I'm going to append itself to GS. Now some of you are saying, what? How's that working? Well, remember, when you have a single equals there, you do the right side first. It doesn't matter that it's the same here and here. You do the right side first, always, right? So on the right side, whatever the vector Genie.scores is, GS will always be a single value. That's going to be concatenate into a vector. That's going to concatenate into a vector. So Genie.scores will become a vector in that case, all right? So what happens, no matter how many values are in Genie.scores, GS will simply just combine into a new vector, and that'll overwrite this Genie scores. And that's how we're going to keep scores off the values. So now we're ready. We go ahead and rerun this. All right, type in Genie scores. Bam. I got all my Genie scores for all my unique values now, guys. See that? I got them all.